calculus integration. So, as per the terminology is integration means addition. Okay. Then why there is a term called calculus? It is very similar to we have calculator and we have computer. So that also compute and this also compute. If I take only the ALU, then both are same. Okay, so now calculus integration. How we do the integration and how we do the addition and how it is different from actual addition. So, what is addition and what is its different way to calculate the addition? Like, if I start with the collection. So, if I collect 5 balls in 1 hour, so now I don't have any ball in my hand. And after 1 hour, if I see, then I have 5 balls in my hand. So 2 hours, 3 hours, end of every hour, 5 balls gets added. What about at the end of 12 hours? Okay, so 5 plus 5 plus 5, 12 times. Okay, that would come to around 60. So addition is collection. Every time duration we collect something, and at the end of some particular duration we see how much we have collected. Now this is one way to add 5 plus 5 plus 5 plus 5. There are many ways to add. Another way to add is 5 into 12. Okay, so we call it multiplication. First is addition. Another way to add is multiplication. So multiplication is addition only when it is uniform. There can be another way of addition. First our collection is 5. Next our collection is 10. Third our collection is 2. How much collect? 5 plus 10 plus 2. That is 30. Now I cannot do a multiplication. 5 into 3 or, okay, so 5 plus 10 plus 2. So that is 17. Okay, so I cannot go for multiplication because it is not constant. So if addition is constant over a period of time, then I can go for multiplication. Otherwise, I have to keep adding one by one, the way we added like a histogram kind of fashion. What about 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7 plus 8 up to 100? Okay, I think it is very big. 1 plus 2 plus 3 plus 4 plus 5 up to 10. Okay, so 1 plus 2 is 3. 3 plus 3 is 6. 6 plus 4 is 10, like that up to 10. Only 10. Okay, I believe no one would dare to do that. It is that difficult. So, this is another way of one addition we saw that we can add. If it is constant, then we can multiply. If it is like this, 1 plus 2, so it is growing. So, first our collection is 1, second our collection is 2, third our collection is 3, fourth our collection is 4. What is after end of 10? So there is a funny way to do that, like 1 plus 2 plus 3 up to 10. If I write, this is one line. In next line I can write 10 plus 9 plus 8 plus up to 1. And then I can add it. So it will become 11 10 times. So 11 into 10 by 2. Okay. So that is 11 into 5. What is 11? What is 10? And what is divided by 2? What is multiplication? What is if I keep on adding? Okay, what are those? Is there any similarity among those? We go for permutation, we go for combination, we go for many Fibonacci series and so on. What is common among all this? Okay, so that I can say now I can do all the form of addition, multiplication, addition, and now we describe the series 1 to 10, and we reverse 10 to 1, we added, and then 11 into 10 by 2. Can we draw a graph? Okay, so like in 1 hour, I collect 5, next hour 10, then next hour 2, then 5, 10 and 2. So in 3 hours, this is the graph. So 3, I would say 3 rectangles are coming into the graph connected. If I get the area of this rectangle, then I am done. 5 balls per hour after 12 hours, 5 balls up to 12 hours, 5 into 12, that is also an area. 1 to 10, so it is growing like this. Okay, it is a triangle. If it is a triangle, then if this is a triangle, then if I copy paste the triangle again in reverse fashion, it becomes a rectangle. And if it becomes a rectangle, its area is width by height. That is 11 into 10. So first is triangle 1 into 1 plus 2 plus 3 up to 10, because it is increasing, so it forms a triangle. If I copy paste, if I multiply it by 2, in next row I place 10 into 9 into 8, then it is 2 triangles opposite to each other. And it becomes a rectangle, and which has one side is 11 and other side is 10. So if I know the area of a rectangle, then if I divide it by 2, then I get the area of the triangle. Okay, so what is common among everything? Means all forms of addition. Area. If I calculate the area of whatever addition, we draw the map of addition where it would vary, the kind of the independent variable is like time, the way we talked, and dependent is its values. And if I draw an area, and if I draw a curve, and if I get the area, I get the addition. One form is multiplication, I am sorry. That is integration. We are talking about calculus integration. Calculus integration is nothing but a form of addition, where addition is calculated through area of the graph. So whatever we want to add, we draw. So one axis, x-axis, we take as independent variable like per hour collection, per day collection, per second collection, and then its values we draw. Sometimes we call it speed also. Like a man is walking, he is collecting 5 kilometers every year. A man starts, and at the end of 1 hour, I see he has collected 5 kilometers. At the end of another hour, he has collected 5 kilometers. At the end of 6 hours, how much he has collected? So, x-axis up to 6 and y-axis 5, 5, 5, 5. So, it becomes a rectangle. 5 into 6. So, 30 kilometers he has collected. 5, we call it speed also, rate also. 5 kilometers per hour. 5 kilometers per hour means every hour he is collecting 5 kilometers. Okay. 1 hour, 2 hours, 3 hours. At the end of every hour, okay, so collection grows, net collection grows. How much is the net collection at the end of 6 hours? So, or he collects 1 kilometer at the end of 1 hour, 2 kilometers at the end of 2 hours, and 3 kilometers at the end of 3 hours. means at the end of 3 hours, total collection is 6 kilometers. If that is the way, at the end of 10 hours, how much he has collected? It is equal to what we talked, 1 plus 2 plus 3 plus 4. So, it becomes the area of the triangle. Okay, so now if we know that everything, every path, every route in addition, they meet in area of the shape, then can we go for more analysis? Means when I know that every river meet at this point only, then I can do research on that water rather than collecting from everywhere. Okay, so what progress we can make? How it can help us just getting the area of something. So for a person, like we talk 1, 2, 3, 4, a person is walking or collecting distance and it is not smooth. It is not constant, like 5 km per hour. Okay? It is very intricate, means he is changing. Like we talk 1 plus 2 plus 3. So we call it x. If horizontal axis is or t, time while we are collecting, then independent variable is t, then dependent variable, how much kilometer per hour he is collecting, that is also t. So at the end of 1 hour, he is collecting 1 kilometer. At the end of 2 hours, extra 2 kilometers he is collecting. So it becomes like you can say ramp. Okay. So in that case, now what would be how much he has collected? So I would say if it is x, then it is a triangle, or it is t, then it is a triangle. At the end of t hours, if I make it a rectangle, then it is t square, half t square by 2. So I can say, if I integrate t, equation of t, at the end of t hours, it is t square by 2. If it is constant, like 5 km per hour, so 5 is constant. At the end of t, it is 5t. Someone says that you just did the multiplication. So, if it is a constant, then just we put t. If it is not constant, if it is a t, then t square by 2. Like that, we do calculation of some few basic things. Because bigger thing, they sit on collection of basic things. Okay, there is nothing new. Like addition, multiplication, then we'll go for exponential, logarithmic, sine, cos, tan. Everything would sit upon the simple things. So if I know this way, if I calculate a few basic things of the integration, then bigger things we can get. What about someone is working in a sine wave? He started from the 0 and then his collection grows, and at end of pi by 2, at that moment pi by 2, total collection is 1, or I can say at that moment, at the pi by 2, he was collecting 1 km per hour at that moment. Okay, since it is smooth, okay, line is highly intricate, means any moment it would change. We were talking about every hour it is changing. Here, every moment it is a smooth curve. And after pi by 2, his collection per hour, means whatever you say, per moment is decreasing. And at pi, his speed is 0. So how much he has collected? Then after pi, since it is a sine wave, it is negative. Negative means he is coming back. And at 3 pi by 2, okay, his speed is -1. Means again he is at peak of his speed. And okay, how much net he has collected up to 3 pi by 2. And at pi, he came back. So total collection is 0. Because area is 0. Plus half minus half. So now if we learn calculating the area from basic to complex, so now if I take the sine x equation, it would be variation in x only, or sine t variation, it would be variations of some t plus 1 by t and t 1 by t square whatsoever. So if I know basic, then the integration of sine comes as cos t. Okay. So if I collect, I think I am right. So integration of sine t is cos t. So cos 0 is 1 and cos, I believe it is minus cos t. Okay. So it is one of them, cos t or minus cos t. So if I want to calculate how much he has traveled up to pi by 2 and it is sin t. So at the pi by 2, okay, now area I have to collect. So at the time of 0, it is anyway 0. And so if I say the integration of sin t is cos t, okay, then area between 2 is like any two slices is beginning area and another area and difference. Means I think we will show in the slides. Then the bigger area, that is cos 90. So cos 90 is 0 and cos 0 is 1. So integration of sin t is minus cos. Now it's clear. So 0 minus 1, so 1. So if person walks in a sine wave and up to pi by 2, total distance he is covered is 1. Next pi by 2 he covers 1, so 2 he has covered, and then minus 2. So integration comes into the picture when we add things that is continuously varying and it is managed by some kind of equation. Okay. So anyway, whatever we are doing, all are through equation only. If I say 1 plus 2 plus 3, it is x. Okay, it is a kind of a ramp. Or if he collects 5 km per hour, then it is a flat. But it cannot be smooth ramp. It can be sinusoidal, it can be cos, it can be tan, it can be log, it can be exponential. So if I want to calculate the total addition, then we go with another terminology called integration, and that is nothing but calculating the area of, if I draw the graph or curve of the addition, then during that duration, how much is the area, that is the total correction. Okay, so we will proceed on that and we will see kind of really interesting and funny things that we believe that it is difficult if we do go for a multiplication or simple addition. That will see. Further discussion on integration concepts. So we'll move on desktops. This is Linux Mint. Okay, so integration is simple concept, but if understandability is not good, then it can make life hell, because as it progresses, things will become complex unnecessarily. Okay, so what we have seen, addition is collection of items. We collect item in each unit of time. Multiplication is large scale addition, and integration area based addition. Okay, so this is kind of continuous addition, that is also it is called. Like if collection of balls is 7 every day, after 5 days it is collected this much. So 7 plus 7, okay, so that comes to 35. Or if collection is ball is too many, like for 395 days it is collected 7 each day, then addition is not possible and it comes to into 398, that is this much. Okay, there can be many ways we need addition. So this is large scale addition, this is small scale addition, so we'll go for addition. Large scale addition, that is multiplication. This can be one funny way also, like 1 plus 2 plus 3 plus 10. So we can write like this and we can reverse and we can write like this. And if we keep adding, then it will become 11 plus 11 plus 11. So 11 into 10 times by 2, because we have added one more line. So net is 11 into 5, that is 55. So it is far easy than someone start calculating 1 plus 2 plus 3 plus 10. He'll go mad. And if it is bigger, then just you can think about it. Okay. Okay. So, so far we have seen like this, okay. So if we see graph wise, so we demonstrated unit wise, and if we see graph wise, so collection of 7 oranges, okay, for one day, second day, third day, for 5 continuous days. So this can be a graph, and this is the scenario. So 7 is a kind of a constant, and everyday collection is constant, and for 5 days, so this will be a graph. So if I calculate the area of this graph, then it comes to 7 into 5, x into y. So that much is collection. So area of the graph is nothing but multiplication, or means this is how the addition in graphical form. Or a person collects 5 kilometers every year, then at the end of 7 hours he collects 35, because x is 7 and y is 5. So 5 into 7 comes to 35. So this is also a way of addition. So if I know this is independent variable, x-axis independent variable, okay, so time just passes through, and y-axis is how much kilometer he is collecting, means he is walking. Okay, so this is dependent variable, and if it is constant, every year the collection is constant, then it will lead to this kind of a rectangle, and calculating the rectangle is nothing but the total addition, total collection. So that we can say 5 plus 5 plus 5 7 times, or 5 into 7, whatever comes to mind. So this is sometimes referred as kind of speed also. 5 kilometers per hour is speed. Actually it is 5 kilometers total collected during 1 hour. So that is also called 5 kilometers per hour. Okay, so 3 cases we saw. This is addition, this is multiplication, and this is what we saw, 1 plus 2 plus 3 plus 4 plus 5 plus 6 up to 10. So these are drawn in a graphical form. So there can be in first hour collection is something else, second hour, third hour. So this we cannot use multiplication. Means this is not a kind of homogeneous. It is not a smooth. It is not same every duration. So multiplication cannot be used. Okay. So this is purely addition we have to use. We have to add this, this, this and this. Okay. So this is. So this is addition. This okay, so this is addition. whereas this is multiplication, it is constant multiplication, and whereas this is, we can say, just addition, this is also addition. Okay, but the way it is done, that we have already seen, so it can be added in this way. Okay, so these three we saw. Now we'll proceed. So we'll proceed towards low. If I know the calculating the area, but all three are based upon the area. This is the first case of the area. Okay, the way we calculate the addition is different. Here addition is calculated like this. Here addition is calculated like multiplication, where here addition is calculated in another funny way. But we can, if we go, but all can be represented through area, and if I get the area, then total addition is done. So that is the scenario. Okay, so we'll proceed more on it. So suppose this is a full rectangle from right to left, irrespective of the color. Now this color is growing. Okay, so this color at a moment it is at x, where x is moving. Okay, now what is the addition till x? Okay, so at x is here and x will be here. If x is here, sometime later, okay, so x can be okay, so sometime later x can be here. Now this is growing always. The way we have drawn, this is growing. So x is shifting one place to other place. So what is in discussion now is at any x, what would be this addition or what would be this area? So I would say, if it is 5, if this is 5 km per hour, or we can say equation as 5. So we can say this as, if this is x, then this can be denoted as fx. Okay. If that is x, so this can be denoted as fx. So for varying x, what would be the area? So that is nothing but 5, that is 5, fx is 5. So x is independent variable and fx is dependent upon the x, and it is a function. So function is 5, it's a constant. So 5 into x is the area. Now we can denote it as like this also. Or we can write like this also, but actual denotation is this. So 5, we would integrate up to x. This is integration. Means integration is nothing but calculating the area, and that area where, okay, so this is dependent variable and this is independent. So independent is range. Okay, now it is 0 to x, from 0 to x. So we can say just x, and fx is 5. So we can insert fx in between. Now I can write here okay. So can we see that 5 into x okay. So can we see that 5 into x, so 5 is fx and this is x. X is independent variable and this is dependent variable. Dependent variable came inside and independent variable went up. So this is how multiplication, or we can even change it more. Okay. So now I would say equal to okay. So I can write here as five plus okay, like this, plus 5 plus x times okay. Now first we have addition 5 plus 5 up to x, up to sometime, that is converted to 5 into x. It is added up to x time, that is converted to 5 into x, same thing. Now it is converted into integration kind of notation, nothing more. So 5 is converted to fx and x become like this. Fx is nothing but 5 only. So it is like this, and then it is 5 and x. So we add dx. Okay, just we can say that just as a kind of, we believe that it is varying in x direction, nothing more than that. Okay, now same thing. Now a person is walking 5 km per hour, and between x and y, how much he has walked. Okay, so that is the area. That is 5 into y minus 5 into x. If I say 5 into y, this is this area. 5 into y is this area. And if I say 5 into x, then it is this area. So 5y minus 5x, same thing. So first is bigger area, next is smaller area. So if I do the subtraction of these two areas, then it leads to this area. So this much he walked between yr and xr. So now I can say 5y minus 5x. 5 dxy minus 5 dsx. This is nothing but, this is not a natural way. This is the notation. This is how integration notation is mapping to the area. So we are learning how integration notations are. So 0 to y is this area, bigger area, and then 0 to x, it is smaller area, this area, what we see in green color. If I do subtraction of these two, then this would lead in between area. So now I can write in integration x to y fx, that is 5 dx. If someone is writing 5 dx x to y means up to y one area, up to x one area, and then subtraction, that is intersection area. Okay, so this is clear. Okay, so now we'll see another form. So basic form we saw that if it is a kind of a rectangle, if it is a constant, this speed is constant, then it is a rectangle, whatever speed is varying. Now it is moving, the person is kind of moving at a speed of 5/2 per hour, means at 1 hour his speed is 5/2, that is 2.5, and at 2 his speed is 5. Okay, so he is accelerating, means he started from the rest and then he is walking, he is increasing his walk speed. So it's not like this, it is constant. Okay, so we are seeing a third form, like we saw that addition is nothing but area. Then this is one form of addition when it is not constant, where multiplication is constant, and where we saw one funny way of addition that leads to a triangle where it is 1 plus 2 plus 3. So this triangle we are talking now. So a person's speed is not constant, speed is growing. Speed is growing at 5/2 per hour. Okay, how much distance he has collected in 2 hours? That is the area. If he is collecting distance at a speed of 5/2 into h is this axis. H is independent variable, and fh is 5/2. So fh is 5/2, then if I calculate this area is total distance traveled by this person in 2 hours. Okay, how much distance he has traveled in x hour? Okay, so that would lead to a bigger area that he has traveled in x hours. Okay, so how much he has traveled in x hour is full, or rather I can say how much he has traveled in x hour is full. Okay, so in 2 hours, he travels this area, then in x hour the full area he has traveled. Now we have to find. Now if I see closely, then this triangle, and if I make it kind of opposite, then this triangle, both are same, means both have same area. This full leads to a rectangle. From here to down it is a rectangle, and rectangle height is 5/2h. At any moment height of this rectangle is 5/2h, and at 2 second hour it is 5, otherwise it is 5/2h. If it is 5/2h, then area of rectangle is 5/2h, that is the height, into width h. Now if I talk about the triangle, then divide by 2. So area of this triangle is area of the rectangle, divide by 2. In integration notation, we can say that, okay, so this is for any h, we want x. So I can say fh dh and up to x. We want to calculate up to x. So fh is 5 by 2h. So f5 by 2h dh up to x. If I take out 5 by 2, then h dh, only variable inside. This becomes this because I know this. This becomes this because already I know this. This is the rectangle. So this becomes this. If this becomes this, can we come to a formula where x to the power k dx, if I calculate the integration, it becomes x plus k plus 1. That is what we see here. K plus 1 and by k plus 1. Okay, so h to the power 2. So we started with h to the power. So if h to the power 0, if it is h to the power 0, so in rectangle it is constant. So if it is h to the power 0, then it becomes 0 plus 1, 1 and 0 plus 1, only x. So that's what we saw. So this area is only x. So 5 dx, okay, 5 dx is nothing but 5x of this integration. So that becomes only x. If it is 0, if it is 1, h to the power 1, this is what it is, then it becomes h square by 2. That is x plus k plus 1. So for k is 0, it is valid. K is 1, it is valid. So this is the area. So what we are trying to find is what is the integration for the basic shapes. So if it is constant, if it is a rectangle, then it is the constant. So it is x. If it is a triangle, then it is x square by 2. So we come to this. So this way we can deduce a kind of integration of basic shapes. So bigger shapes, they are derived from integration of basic shapes. Okay, now what is the area between any x and any y? So as per the integration, okay, now the way we talked here, between any and x and y, so this area between x and y we have to subtract. So that is the same thing we'll do. So this is the formula. So area between y minus area between x, that will lead to x to y fh dh. So that will be 5 y square into 2 plus 2 into 2 5x square. The way we deduce the formula. So integration between x and y, any x and y, please don't concentrate on dh. dh just say what is the variation. Okay, so we can remove dh also. So if I see this integration of 5 by 2h between x and y, so that is for y and then minus for x. So this is what we have seen here. For y whatever we get, for x whatever we get, we have to subtract. If it is x to y. So we subtract and we get like this. So now we have complex shape. If it is complex shape also, everything, all the basics there, it stands same. What about sin t? If variation is, now a person is walking and he is reaching apex here, means maximum speed, then he is decelerating. He is reducing his speed and at pi r his speed is 0. How much distance he has traveled? So if this equation is sin t, then it is nothing but 0 to pi sin t. So if I say that integration of sin t, the way I say integration of xk is xk plus 1, if I say integration of sin t is minus cos t, then integration of sin t, whatever we see, 0 to pi. So that will come as minus cos pi minus cos 0, that is 2. So this person has traveled 2 kilometers if he travels in this fashion. If he travels constant fashion, then it is just area of that. Anyway, area of everywhere, it is area of rectangle. If he travels this way, then area of a triangle. And if he travels his sine wave, then area of the sine wave. So that is nothing but is integration, and then upper limit and lower limit we have to subtract. What about this? A person, he is walking, okay, and then from pi to 2 pi he is walking like this. So negative walking means he is coming back. Okay, so negative walking is coming back. Okay, positive walking means he is walking forward, whereas negative walking means he is coming back. So this is the question. So if it is like this, what would be, how much distance he has traveled? So from here to here, he is walking forward. From here to here, he is walking backward. So here, total distance he has traveled is 0. Here, total distance he has traveled. Then here, he has total distance he has traveled separately. But if we calculate both, add both, it is 0. That is sin t dt from 0 to 2 pi. So cos 2 pi minus cos 0, that becomes 0. So it is perfect. The area is perfect. Now in better interpretation we see, so person is walking forward in this duration and person is walking backward in this duration. If that is the case, then total kilometer walked is 0, whereas for 2 pi he walked 2 kilometers. So in this reason we say he walked, even though he walked 2 kilometers back, but it is minus 2. So minus 2 kilometers. Okay. So that is okay. So this is how it is. So we'll see the lapses. So we started with kind of addition is collection of items, multiplication is large scale addition, where integration is smooth addition, continuous addition, or area based addition. This is simple addition. This is bigger addition in the form of multiplication. This is another way of addition. So simple addition, okay, that if so, addition in the form of area, that becomes multiplication, and various forms of addition. So this is discrete form, we can say. This is continuous form. This is another discrete form in a triangle shape. Okay, how addition, we started with addition, it shifted to multiplication, then it shifted to integration. Integration is nothing but just giving a sign, but it is internally it is area. So this integration slowly leads to this. Now integration is finding the area. We can find area between a range. So that we can denote like this, x to y and its function. Okay, so integration fx is the dependent variable and x is independent variable. So independent variable we also call range. From one range to another range, that different we denote like this, x to y, and y f5 is fx. If fx is triangle, then it is like this, and then it leads to a formula of a triangle or any x. Okay, we can have a range in triangle also. Then we went with another formula, that is sin t, and we found the area, and then we say how much kilometer this person has walked. Okay, so we'll see lab. We saw various facets of addition. I mean, it's kind of laughable that we are concentrating so much on addition, but fortunately or unfortunately, all the big things, they are based on addition. So addition is very big thing. Okay, like we can add things like one by one, or we can, if addition is smooth, in the sense that it is continuous, like 5 into 5, 10 times, 12 times. Then we go for multiplication, or we have seen other ways to add for addition. But the common thing among every type of addition is calculating the rectangle. And we saw that if we go by rectangle, then slowly we move to kind of mathematics where we have kind of a line function algorithms and these kind of scenarios. So we have independent variable and we have dependent variable. Generally, independent variable we draw on x-axis and a y-axis as dependent variable. And if we describe that, like if x is an independent variable and fx is independent, then based upon the fx, we draw the kind of graph and we calculate the area and we get the addition. If we want a part in the area, okay, like how much is the area between this and this, then we can calculate full area of the second part and first part, and we can do subtraction, and then so that is called integration, kind of lower limit and upper limit. So that we saw. So yes, we kind of it's pretty nice. Like we have a theory, we have all the science, but it needs corroboration. It needs to be proved. If I am saying that calculating area, calculate for one like sine wave we achieved, but little more if complex if we do, then probably kind of it will be more useful. So we'll see lab session, like suppose that I have a kind of sphere like Earth. Okay, so I have Earth map, Earth globe with us, and I'm searching for a place. Like I'm searching for a place called Al-Qaeda, and it is in Egypt. So wherever the globe is, from there it would rotate and it would stop at a kind of longitude that meets the Al-Qaeda. Then it will rotate. And then it will kind of twist in through latitude, and it will show the Al-Qaeda at the center. So this is the requirement. Okay, so it's not very difficult. We can rotate, and where the longitude of Al-Qaeda, there we can stop, and then we can kind of tilt again for the latitude. Okay, but what is kind of limitation is that whatever we are searching, like globe is at one position, whatever we are searching, okay, that should reach in constant, like I'm saying in 5 seconds. Okay, like I am making some video, and prior to the video, I am showing where it is. So depending if it is very far, it should not take 20 seconds. If it is near, then in 1 second. So it should take constant time, like 5 seconds. If I am showing a place in kind of Siberia, or in one place in Alaska, or one place in Antarctica or Australia, okay, everywhere it would take same time. If it takes same time, then rotation speed will be different. One thing. Second thing requirement is that Earth should not rotate at a speed and suddenly it should stop. It should start with the high speed and gradually it would lessen the speed, and where it meets the longitude, then it will be almost zero. So that someone should see slowly that it's like a train, that it cannot stop at a station immediately. Means from some distance it will start kind of reducing the speed, and then it would stop. So that way it will start at very high speed and it would reach the longitude at almost, it would stop right there and it will keep decreasing the speed. Okay, so I know how much time it would take to reach there. Okay, I know longitude I know the longitude where at the beginning the globe is and where it has to come. What is the initial speed? Now, when I talk about x and fx, then I am considering fx as minus x. Okay. So, initial speed is kind of minus x means if it is 10, okay, rotation is in whatever a unit it is, 10 unit per second, then next second it would be 9 and 8, or it has to finish in 5 seconds, then 10, 8 and near 5 seconds it would be almost 0. Okay, so it is kind of reduced in a linear manner. We can go for kind of sinusoidal or x square or what, but right now requirement is minus x kind of thing. It will reduce like a ramp. So if I know that it should reduce like a ramp and I know total time, I know what is the initial longitude and final longitude, can I find the initial speed at which globe will start rotating, and then second by second it will start rotating slowly, and at the end when it reaches, then it will be almost. Okay, it is similar like a person is walking, okay, and like he is in market and he is walking to home and he has only 10 minutes. But problem is the way human walk. Initially they can walk very fast, but gradually they decrease the speed. So if he knows that he has to kind of walk maybe 2 kilometers, and 2 kilometers he has to reach in 10 minutes, something like that. Then at what speed he should start his walk, so that if he gradually reduces his walking speed, then by the time he reaches the home, he will be kind of at the rest. Okay, so that is the question. So how we can find this through? So we want to know the initial speed. Okay, because final speed we know 0. Time derivation we know that in 10 minutes he has to reach. Distance we know. What would be his initial speed? So that will calculate through integration, and then we'll know that how useful it means. We cannot do by any other means. Okay, simple addition and subtraction would not work. Means power injection is required to come to this. But this is the simplest in integration. Okay, if fx is not minus x or similar to that, then it can be much complex to any degree, and later it may reach differential equations and those kind. But still, if we have started integration, then this one will see. Okay, so as per discussion, we'll move to lab session. So prior to lab session, I believe I can share more things. Okay, so whatever we have covered, so I would summarize because it will kind of little complex now. So what we have done is now we have some kind of understanding in integration. If it is constant, then it is rectangle, and if it is a ramp, then it is a triangle, and so and so. So what we have seen, like if we have a fx and dx, we consider it as fx ds from 0 to t, and now it becomes fix, that is the integrated value, and it ranges from 0 to t. So this is what we have seen. I think we can add more to it. Okay, so here then post that, so it will be like post that it would become like okay, integrated value, and x would be replaced by 0. So this is the default nature what we have seen. So ft minus f0. Okay, so finally it would lead to f integrated t minus f integrated 0. Okay, so this is what we have seen. If I have fx dx, it would convert it to fx ds 0 to t, and fix, that is integrated one, and t, then fit minus fi 0. So upper limit minus lower limit. So this is what we have seen. Now if I just say integration of the dx, then it becomes like x to the power 0 dx, and it is x. And if I say integration of x1 means x dx, it becomes x square. So this is triangle. This is triangle, area of triangle, and this is rectangle. Okay, so rectangle in the sense that x into constant. Now constant is 1, so only x, and here x square by 2. So now with this we come to a conclusion like if it is x power k dx, then it is x to power k plus 1 by k plus 1. So as I stated, the integration starts with kind of smaller things, and then slowly it leads to kind of complex items. Now we'll move for kind of sin x and cos x. So sin x, sin x series is x minus x cube plus x5. This is the sin x series, and this is cos x series. Now if I do sine of t1 to t2 sin x dx, then now we'll do one by one. So x would change to x square by 2, x3 would change x to the power 4 by 4, and 4 into 3 this combination, then it would become like 3 factorial, so it would become like 4, and then x to the power 6 and 6 factorial, and x to the power 8 and 8 factorial. So it would become like this: x square by 2 minus x to the power 4 plus x to the power 6, and t1 minus up to t1 to t2. So since integration is an area, so it has a range. Area cannot be in single dimension, so it has a range. Now for cos x, if I see, 1 minus x square. So this is what it is. So whatever we have achieved here, so that is from here to here. This is what we have achieved. So full, if I take, okay, so on left side of equal to and cos x I bring right side, then it becomes 1 minus cos x. So integration of sin x dx is 1 minus cos x. Now t1 to t2, so that leads to 1 minus cos t2 minus 1 cos t1. So minus 1 and plus 1, so becomes 0. And this is minus cos t2 minus cos t1. This leads to minus cos x. If it is minus cos x, then t1 to t2, if I say, then it would be minus cos t2 minus cos t. Okay. So finally, the integration of sin x is minus cos x. Now what is integration of cos x? So 1 would become x square would become x to the power 3 and factorial 3. X to the power 4 would be x to the power 5 factorial 5. So it is same. So integration of cos x is sin x. So we can see we started with a constant, started with a rectangle, and we came to a formula, started with a triangle and we came to a formula, then which led to a kind of a common formula. With that we calculated for sin x and cos x. So this is the integration. So this way we can find for exponential, logarithmic and so many things. So if anything depended upon sin x and cos x, so we know what is the formula. So from the base stuff, so that's why it is said that in mathematics the most basic thing is addition. So from addition, multiplication, integration, then integration of constant item, then variable item, slowly we came to sin x and cos x, and then we'll move for too complex. Okay, anyways, so now we have seen that if I have a triangle and which has equation as, now we came to a kind of independent variable and dependent variable. So if dependent variable is phi 2 by h, then how we find the area? Now in lab session, as per the discussion, okay, so a man is walking and he knows that he is in a kind of market and he is coming to home, and he would start at y kilometer per hour speed and he would decelerate at a kind of a constant rate, and when he reaches his home, that is after d minutes or seconds or hours, whatever, his speed is 0. Means he came to normal, means he just reached his home. Okay, he started with a high speed and slowly he reduced his speed at a constant rate, and when he reached his home, then his speed is 0 and he took d unit. Okay, if that is the case, then at what speed he started if he has to cover a distance? Okay, now this person knows that he has to travel a distance kind of 5 kilometers, and 5 kilometers he has to reach in 2 hours. Then 2 hours means d equal to 2. 5 kilometers he has to travel. Then y is the initial speed. At what speed he has to start, so that when he walks for 10 kilometers, after d hours, he'll come to rest and he enters the home. So, okay, so if that is the scenario, can we see this is the equation of a line? And if this is speed, then if I integrate it, then area becomes kind of total distance. Okay, so this line is equation of a line. Okay, so this line is equation of a line So this line is equation of a line So this is a line now. It should be pretty clear. Now this is a line. This is a line, and this is the kind of it talks about speed in the sense that at any moment how much distance he is collecting, the way we discussed earlier. At any moment how much is the distance that he collected. So that leads to speed, and if I see speed at 0 is y and speed at d is 0, and this is a line, can we come to a kind of equation like this? 0 minus y by d, t is any time plus y. So this is the equation of the line. So, okay, if time is 0, okay, this whole stuff becomes 0, and here the speed is y. If time is d, then d by d is 1. This leads to minus y plus y equal to 0. So at time d, here speed is 0, and at time 0, speed is y. Now I have to find the area. If I find the area, I would say the distance covered, how much distance he covered in d time. So area of this from 0 to d. Now the way what we have seen, okay, so now we can denote it as ty dt. I would rather say it should be in braces. Okay, so it is in braces, where we see. Okay, so complete equation dt means we change it to dt, means this is what the fashion is. Whatever is the variable, so t is variable, so we call it dt. Now, if I see the integration, then integration of the t is t square by 2. So this becomes like this, and yt d to 0. So this will become minus d square by and this much. Okay, so now if I take out y and then we do shuffling, then initial speed would be distance covered into 2 by d. Okay, so this 2, I believe this is what is correct. So y if I take out, okay, I hope this is correct. Okay, so y, the initial speed is total distance covered by d if it is reaching in d. Okay, now what about now we talked about D. What about its speed? Okay, so we talked about at what speed he would start. If I know he started at speed y, then how much distance he has covered at any moment t. So this is the distance total covered at t. So at any moment t, so this is the distance covered. Okay, so this is what anyway we have seen, but it is crucial because this is our lab session. So in lab session, what we'll see is we'll place longitude and latitude of a point in Earth, and Earth should start at a speed that is y, and it has to rotate till it reaches the latitude and longitude what we have specified, and when it is reaching at that point, the speed should tend to kind of zero. It would very slowly it would reach this point. Okay, then this is secondary thing, that it would rotate again for latitude and then it would show it. Okay, that also we can manipulate speed wise. So initially the latitude movement also will be at high speed if it is up, and then it will slowly come here. So how much distance we are traveling? Can we see? This is not a linear distance. This is angular distance. So suppose that Earth is at 0 beginning and longitude is 170, then it has to rotate 170 degree angle. Okay, so distance covered, we are talking about distance covered. So we know distance covered, like here we know distance covered is 170 degree, or we can make in radian, into 2 by how much time it takes. So idea is it should take constant time. Okay, like if it is reaching this point, okay, or so if it is moving 170 degree, or it is moving 720 degree, or it is moving 340 degree, okay, it would take same time. If it is taking same time, distance is different, and then certainly it has to start with a different speed and then slowly it would reduce. So that we'll see in lab session, that how actually it look. But this is the concept that we'll follow. So first is we'll know what is the initial speed, and because we know total angle it has to cover, and into 2, and how much time it has to face. If total distance to cover is very high, otherwise these are constants, so in beginning speed will be high. Okay, now every moment the globe is rotating. Now I know y. Okay, I know t because I know how much time has been spent, or time span, how much time span is over. Okay, and what is the total time, that at any moment we can calculate how much distance it has traveled. If I know how much distance it should travel by this time and how much distance it has traveled by now, then it would help us in rotating the globe. That's why there are two diagrams. First is to find the initial speed, and second is to find the distance covered at any moment. If these two we know, then we can begin with the initial speed rotating the globe, and after that any moment we can see how much it has rotated and how much it has to rotate by now, so we can quickly rotate that to that extent. Okay, so that we'll see in the lab session. Okay, so we'll proceed on the lab session. So as per the discussion. Okay, so I have a Python written program, and in the program we are doing the same thing what we have stated. First we calculate the kind of what would be the beginning speed, and then based on the beginning speed every moment we calculate the speed. So it is not very difficult. So we calculate the y. Okay, so y being the beginning speed, and then as time passes, so we calculate the how much distance it has to cover by that time, and how much distance it has already covered. Okay, whatever the diff is, we add in the angle of rotation. This is what we are doing. Okay, so we'll try now. Python 3. Okay, and then we'll give a longitude and latitude. So anything we can give. I have latitude, longitude of Australia tip north. So there are few I have. So I can just say what I have here is. Okay, like here text one. So I'll just copy paste this. So this is one that is Australia northeast tip. And these are typical points. So it is south. So I'll say minus, that is latitude. And this is east. So I'll say plus. So then I can click. Okay, so time duration is 40 seconds. This is what we have set. And it should be bigger, I believe. The image is too low. Okay, so time is 40 seconds I have given. So beginning speed will be higher. And we will set it bigger. So kind of 112, and width is some 700. Okay, so this is the 40 seconds it has to complete. So one round it will make, and slowly it has to slow down. So it is linearly slowing down. Now it has made one round, so it will be slower. It is really slow. Okay, so smoothly it is slowing. Okay, so this is what it is. So I can reduce the time. So it will be quicker. So I don't know how much it will show up. So I'll make it kind of 4 seconds. So it would be very quick at the beginning. Then it will slow down. Okay. So if I make configurable in the sense that probably I can make it as sys.argv3, and here we can set. So I can try for 20 seconds. So it is quicker. Linearly it is becoming slower. Now it will be slow. So when it comes to exact point, then it will be kind of stand still. So that is the idea. Okay, there are other points that there is one more point that we can try. Okay, someone can try with the x square. So we have tried with x only. So linear decrement. So it is minus x. So if it is x square, then it will be curve or e to the power x. So that can be tried. Okay, there are other latitude, longitude. So this is, I believe it is somewhere near Spain. Okay, so it is west. So it would be minus and north is plus. So all right. So one round it will make so that it is becoming slower, and it should stop when it reaches. It is very slow now. So it looks like it is. It is really at some point in Spain. So this is the idea. So at the beginning we saw there is a speed. At the beginning there is a speed. And then a speed gradually slows down. It is much lower. Okay, so we can try with other point. So one more point I have, some typical points. So one point is, I believe it is in United States. It is north and west. So it is minus. Okay, so it makes one round. Now it is slow. It is very slow. Now it is standstill. This is the idea. Okay. So this is how it is. So we can. So a bigger thing would be here that someone can try this as other functions. Okay, but he has to think about kind of initial speed, that because the distance has to be covered in this much time only, and if I go for some equation, then at the beginning speed we have to find. So that is required. Okay, other places also we can try. So we can try some kind of orbit place. So kind of, or same place we can try whatever we did. But we'll change the timeout. Okay, we'll see 60 seconds. Is it really becoming dead zero? This is 60 seconds. It has to complete. So it reached Africa. It crossing India, Australia. So this is one round completed. It has to complete 2 rounds. Now it will be damn slow. So it is slowing. Okay, so I think it is more prominent now. It is pretty slow. So it started with a good amount of speed. See the speed now. It is almost zero, but still it is moving. Still moving. So it reaching kind of. Okay. So this is what we showed. Now I can try in 3 seconds. Or in 4 seconds. It should be very quick at the beginning. Then it is slow. Okay, we can try other map. Okay, we can try even other. So this can be used like in any kind of demonstration. If we want to show the location, then it would move the complete earth and then it would show. So I believe it is worthwhile, probably in kind of some 20 seconds. So first round it is making in 5-6 seconds only, and then rest it is taking. It is stand still. Okay, so I think demonstration is well enough, or I can try one bigger one, kind of 90 seconds. Okay. It is slowing down, so one round is not over yet. I believe it is pretty slow now. Okay, it is dead slow. Completely came to rest. Okay, so finally we saw that integration is nothing but perfect addition. Okay, so we have seen many type of addition, but if we go for kind of if our data is varying kind of every unit, then it is very fine. We can go for multiplication, addition, or other way of doing the calculation. But if our data is varying every moment, Okay, so every moment in the sense the dependent variable has a kind of a function. So if it is a function, then function, like if I have independent variable x and function is fx, then x can be 0.001 and it can be 8.0, it can be 6.955. So when we are looking for this much granularity, then we go for area approach. And now if we talk about the example, so example, we have shown a few examples, and working example we have shown the kind of like a person starts from a particular velocity and he reduces the velocity smoothly, kind of minutely, and reaches the distance and where he is kind of completely at rest. And in this kind of scenario, how we can calculate that if we know that what is the time he should reach a particular kind of distance. So he knows the distance and in how much time he would reach, he would kind of make the distance, and he is reducing his speed constantly, then at what speed he should start. So we showed that example through globe, and we know that how much distance, looking at the longitude and latitude, how much distance a globe would have to travel and how much time it should take. If we know that, then we can start with a velocity, and then with that velocity, if it gradually reduces the velocity and it reaches zero, then typically it will be rest the point where it has to reach. So that we saw. So integration is kind of a calculation in very fine granularity. Okay, now integration is not only limited to software or calculation. So I have a kind of inductor in my hand. Okay, so I tried. So inductor is a sense like it creates a magnetic field. When we apply a voltage across it, or we try to pass a current, if we apply a voltage across it through an inductor resistance circuit or inductor resistance capacitor circuit, whatsoever, then current would try to kind of flow through it as per the nature, but it will induce a magnetic field. Since it has so many coils, we can see that is rounded across a kind of core iron. So it will induce a magnetic field. If it induces a magnetic field, so it is kind of inertia, and means it has some strength. Okay, so it is not a kind of normal wire. So if it has a dense magnetic field, then it will oppose the rise of current. Okay, so that is the scenario. So if it is also more powerful the inductor is, more powerfully it would oppose the rise of the current. So voltage across the inductor, okay, so initially it will kind of behave as open circuit. Capacitor behaves as the open circuit for voltage. This behaves as the open circuit for the current, and then there will be kind of high voltage across it, and then current would start slowly flowing. Means the inertia of this kind of device will be overpowered by the battery, and then at the end this magnetic field would not work and current will start flowing completely and voltage will drop. Okay, so if it is only guy that is connected, so voltage would drop in the sense that voltage across this in LR circuit. So it should be like there is a wire, so there should not be any voltage, and current should be maximum. So it will behave like a, so at the initially it will behave like open circuit for the current, and at the end it will behave like a closed circuit for the current. Okay, and if we talk about the voltage across this time to time, then it is the L, that is the inherent, it is measured as L, it's a unit of the inductor, L into di by dt, So at any time, what is the rate of change of the current? So if rate of change of the current is high, then voltage across it would be high, and rate of change of the current is low, then voltage across it would be low. So at the end, so there won't be any change in current because current is constant and full current is flowing. So voltage across it would be 0 as L into di by dt. So di by dt is no change in current, so it is 0. And in that case, the voltage across it is 0. So di by, but I is maximum. But problem with this we could not do as the inductance is in kind of the micro or millihenry, and the tau, that is time constant. So time constant, if I say 5 into time constant, in that period it should reach, the current should reach its maximum. So that comes in millisecond. So that much, so for that we need a kind of function generator and oscilloscope to measure that. So we have kind of, we show that. So we have a kind of a very simple multimeter. So what we have done is we have taken a capacitor. Okay, so it is a capacitor, and this capacitor is from some company Maxcon, and it is written as 1000 microfarad 15 volt. So it is operating voltage is 15 volt, and 1000 microfarad it is a kind of so 1000 microfarad it is kind of it has value, and 15 volt it operates. So that we are using now, and then as we stopped that current is in inductor. So now we have inductor, capacitor and inductor. So current across inductor kind of it is like so voltage. If I see the voltage across inductor, so beginning will be very high, and okay, so then it will make a exponential down, and then it will be kind of a flat slope, and it will reach to 0. So voltage across inductor, it starts from high, and it follows a kind of exponential curve, and then it reduces to 0. So beginning slope is high, and at the end slope is less. So same thing will simulate through capacitor, and current would be high at the beginning, the change in the current. So if you see the voltage across a capacitor, or if I say current across the current inside the capacitor, okay. So so current is nothing but dq by dt. So charge in capacitor is whatever charge it is storing. So capacitor stores the charge. So that is capacitance into voltage. So dq by dt, that is the current. So current equal to capacitance into dV by dt. So we can say that the current at any moment is equal to capacitance into dV by dt. So how much voltage is changing, that much is the current. So dq equal to C into V, dq by dt equal to C into dV by dt. So current equal to C into dV by dt. So if current is dependent upon the change in the voltage, so initially voltage change is high, so current will be high. At the end, voltage would establish itself as the nature of capacitance. It's a kind of it's a charge storage device. So it will store charge up to its capacity, and then then voltage across it is. So initially it will oppose the voltage as per its inertia, we can say, or it is storing like inductance. I will talk about inertia, but the end it kind of giving in the sense that it stores some energy, and then it gives like a capacitor. At the beginning it has inertia, and then at the end it stores some energy, and then it gives it, and then voltage would reach to maximum. So that is the kind of so capacitor will see with the, now if I see I equal to C dV by dt, then it now if I try to calculate, then V, okay, so I equal to C dV by dt, so voltage will equal to kind of integration of the current. Now we'll come to integration finally. So if I see the voltage at any time, that will be integration of the I. Okay. So now calculus integration comes into the picture. With that we'll calculate how much is the with the formula that how much should be the voltage across the capacitor at any moment. Then we'll calculate the current. Okay, and then we'll draw the graph. We will also calculate the capacitance. I don't think the way it is written and the quality of capacitor, it would be 1000 microfarad capacitor. Size is also very less. So with calculus, we will measure we will verify it is a good capacitor because it should bring the curve as like exponential or logarithmic. And then if it is verified that it is a capacitor, nice working capacitor, then we will find its capacitance also. So that is the scenario. So that is the usage of integration. Okay. So we'll kind of we have everything in the integration from software verification to hardware verification. Okay. So that is the story. So that we'll see. Okay. So we have taken a capacitor. This is a kind of 1000 microfarad capacitor it is, and we have taken one resistor. I think it should be visible. So a resistor is around 56 kilo ohm. I believe we can measure it. Okay, so first we'll see how much is voltage. So we have taken a battery source. So the voltage across battery source will measure. Okay, it is 2.6, and capacitor should be reset. No voltage, and we will measure the resistance. Okay, so it is 56 kilo ohm resistance. Okay, so we'll connect it. Okay, so we have finished the connection. So now I'll attach the battery, and then we'll see the change in current. Current should be it should become 1 or 0. It would take some time because capacitor is powerful. It started with around 46. Okay, minus we are showing it is like ammeter is connected wrongly. Okay, so it has reached 11. We'll wait till it becomes kind of 1. It will take some time. Okay, so beginning was quick, and that is the kind of capacitance behavior, capacitor behavior. But reaching a kind of zero, it would really take time. Okay, so it reached 1, so I think we can stop it, and this is the kind of time duration it took. This is what we'll consider, or we'll wait till it will flip for 0. Okay, so I think it's enough. So we'll disconnect it, and we'll measure the voltage across. Okay, so it is flipping, so I think we are done. So we'll measure the voltage across the capacitor if it is really charged. So white is positive and blue is negative. Okay, it is really charged and it is discharging 2.5352. Okay, this is the rate of discharge. Okay, so it will discharge slowly. Okay, so that is about the kind of a capacitor behavior. Okay, so as per the discussion now, we'll see for the, so integration we have seen for these shapes. Now we'll see the integration through measuring the capacitance. So that is the idea. Okay, so we'll add few slides. Okay, so we'll have a new lab session. So in lab session kind of okay, so as per the discussion now, we'll calculate the capacitance. So this is the capacitor, and we have very small resistor, that is 56K, and then we'll measure it. So how integration comes into the picture, because capacitance is not resistor, so it's capacitance, capacitor varies. So capacitance resistance, we can say the net reactance or net resistance of the capacitance, it varies over the time. So it is not a linear resistance, so it is variable and it varies exponentially. So we'll see, like if this is a capacitor and charge across a capacitor that is stored at any time is C into Vt. So Vt is the voltage that is applied across the capacitor. And if C is the capacitance, that any moment how much charge is stored, at that moment whatever is the voltage into capacitance, that much charge is stored. Okay. Now if I see what is current, so current is nothing but dq by dt. If this is dq by dt, so the charge, okay, charge at any time, how much charge is stored, that is integration of the current. Okay. Okay, so how much charge stored at any point? So that is integration of the current. So if I try to write like this, Q equal to, so that will be integration of the current over the time, I dt. Okay, so we'll get integration sign from somewhere. Okay, so integration sign is a little funny. So this is the scenario here. Okay, it is not pasting at all. Okay, so this is the scenario here. And this is very important. So the charge stored at any moment. Okay, so charge stored at any moment is integration of I dt. So, or current at any moment is dq by dt, how much charge is getting stored. So what is the diff in that? So dq by dt. Okay, so now so all three we are clear. So if dq by dt is I, then I at any moment is C into dv by dt. Now as we talked that if I kind of integration is nothing but calculating the area. If I have a curve whose equation is I and then I calculate the area, it becomes Q like that. So if this is the curve, we can see this yellow, this is the curve of I. So if I calculate this area, okay, if this is the curve of I, then integration, if I calculate the area, this area, so if we have a kind of close watch, then this area here it is less, slowly it is growing, okay, and area is maximum here, complete. This area curve, if I draw, that is Q. You can see area curve is growing. This is area curve, okay, and after a time it becomes stagnant. So this is Q. This is area curve. And this is the area. This is I curve. So if I know I curve, I calculate the area. That area is this curve. It starts from 0 and it proceeds like this. So this is integration. So if I have a kind of a voltage source, current, and it is a CR circuit or C circuit, then I have Q equal to CV. And if I have voltage source, then it is resistance voltage and capacitance voltage. If IT is the current flowing at any time T, then R into IT and QT by C. We proceed, and finally we come to a stage where dt equal to CR by dq. Okay. Now we come to another stage where dt by CR. Okay. Now we have CVS minus QT. Okay. So this is a kind of differential equation. So if I consider CVS minus QT as U, then dq equal to minus du. So finally we come to a equation where dt by CR equal to du by U. Now can we see there are two equations. One equation is dt. dt means dt is a variable. So here the constant is minus 1 by CR. 1 is missing here. So minus 1 by CR. So I am doing integration of minus 1 by CR dt over the time tt. So we are calculating area of a constant. Means time is constant. And here we are calculating area of the U. U is variable where means it is dependent upon capacitance. Voltage across the capacitance. If I see the U closely. So voltage across capacitance is variable and this is the variable. Now if I calculate the area of this, means I get the time and then calculate the area of this, then I get like this, and finally it comes to a kind of equation like voltage across the capacitor at any moment is like this, and T is at any time T CR. Okay, so this is the differential equation. Means we started with this and then like Ri. So Ri, I at any moment is dq by dt and qt by c anyway we have. Now we just shifting left and right. Okay. So dt, now we have two variable dt and dq. So left, right we do and we reach here. Then we kind of, if I see this, okay, two variables there dt and dq. dq is changing. At every moment the charge storage is changing, T is changing. Every moment means moment is changing and charge stored there is changing. That leads to this kind of equation. So there are two graphs, like we kept saying that now we have fx dx. So there are two fx, okay, that come in equal situation. So if there are two fx, then we integrate and finally we resolve it and it comes to logarithmic. Okay, so 1 by u integration is log ln, and we calculated many other integration like cos x, sin x and x for k. If I calculate for 1 by u, 1 by x, it will lead to ln. Okay, I mean if I differentiate ln, it will lead to 1 by u, and then finally ln minus means division, and then if I reverse the ln left side, it becomes exponential, and finally it comes to equation like this. If this is the equation, then current is, okay, if this is the equation, then current is differentiation and it leads to equation like this. It equal to, okay, Vs by R e to the power Vs by R e to the power T into CR. Now, if time is 5 multiplied by CR, it leads to Vs by R 1 by 48. That is 0. Means this is called tau. CR is called tau or time constant. Time constant in the sense at 5 into CR, 5 into time constant. So can we see the graph? This is the graph is drawn based upon whatever we see, like 1000 microfarad capacitor we have taken, and then 2.6 volt battery we have taken. And if this is the scenario, we add the ammeter like this. If this is the scenario, then this would be the graph. So it starts from 0 and then around 210, it reaches the kind of a stagnant value. So we can say that 210 is the time when it becomes like 0. That time is nothing but 5 into time constant. So if I see this equation closely, okay, so if I keep growing the t, if it becomes 5c into r, then it is almost 0. So that is called time constant. Okay, it helps in finding the value of capacity. Anyways, so now we have done the experiment. Okay, so we have done the experiment, and this is the lab session, and we can see this capacitor is connected to resistor in series. Then in series ammeter is connected, so multimeter behaving like ammeter, knob is on microampere, and then ammeter is connected to battery, and then battery finally it is connected here. So in this circuit we went ahead and we calculated the current at in the reading, like initially it is fluctuating and then 46, 45, and these are the microampere that is appearing, and these are the time instance at which this microampere is appearing, and then like this, then we see that 11, so it started with around 46 microampere, and then it reaching 11 microampere at 1 minute, okay, 46 to 11 in 1 minute, and then 0 in 210 seconds, that is 3 minutes 30 seconds. So that much delay it is taking. So now if I see the I formula, this is like this. So we can set up Vs is 2.6, 56 kilo ohm exponential minus t 1 into 56 kilo ohm and 1 milli kind of farad. So it comes to 1 into 56. Okay, so our calculation is, or now we know that 5 into RC is total time it takes to become current as 0. So 210. So capacitance, it is written 1000 microfarad, but we measure it as 750 micro. But anyways, this is the kind of code we have written in Python, and these are the readings we have kind of used in a tuple, and then this is a theoretical Y, and then this is a practical Y, that is the kind of second element of that each tuple, and we plotted like this. So red color is the experimental one, what we got, and it is theoretical. So obviously it is different because we thought it is 1000. Okay, probably we can try with 750 and we see how close it is. We have the program. Okay, so here we have used 1. Now we'll use 7.50. Okay, and we'll try drawing it again. It is exactly same. It is exactly same. Okay, so our calculation is perfect. Okay, so integration is perfect. Means the way we thought about the integration, and this is the crucial point when we calculate the area, calculating the net charge, and then this is the graph we drew considering whatever is written on the kind of the capacitance. So capacitance, it is written as 1000 microfarad. As per the capacitance, this is what we got. But if I change it, then we get exactly like this. It is exactly like unbelievable. Okay, so I mean we can paste it. Okay, so we'll save it. Call like figure 3 and we'll import it. Can someone believe this? Okay, so I can point it that with this graph a theoretical was made. Okay, so theoretical was made like theoretical 1000 microfarad. So theoretical was taken as 1000 microfarad. And I would rather say capacitor means okay, so when capacitance is 1, now in calculation now it is taken as 70 microfarad and they just coincide. So theoretically 750 and practically so means this is amazing. Okay, so 1000 as per the kind of written on the capacitor, and what we believed it is 750 and it is same. Theoretical and practical is exactly same. Means unbelievable. Okay, so this is for integration. We use the concept of integration and we saw the capacitance characteristics and it is perfect. Okay, so this is the lab session. So probably we have finished the integration. So we started with kind of addition, simple addition, and simple addition becomes multiplication when it is too big, and simple addition in kind of in a triangular way. So it can be done like this. Okay, now simple addition, if I draw in a graph, so it is a rectangle. Okay, and then finally we came to three kind of like if I have simple addition, then it's a kind of different bar chart where multiplication cannot be applied. But if simple addition is constant over the time, then multiplication can apply. Otherwise, we have to calculate in this kind of addition, we have to calculate bar by bar. Okay, then we saw that multiplication becomes a integration. So sign we change. So integration only we sign we change, and lower limit, upper limit come in the while calculating the area. So integration is nothing but calculating the addition with a kind of solely through the area of the shape. So now if I have to find a region, that region is nothing but switching the sign, a lower limit and upper limit, and this is the equation of the dependent variable. So this is dependent is flat and its value is 5, so 5 dx. And then we move to triangle where equation is not constant, it is variable over the time. Time is varying, this equation is varying, both. So in that case, we saw that it leads to a formula. So we came to a conclusion that if k is 0, that is kind of a rectangle, or k is 1, then it is kind of a triangle. Then further we came to this formula. So, okay, so if I know the triangle formula, if I want a range between here to here only, not complete, then we have to place a range like this. Okay. Now we calculated so if I know the sign integration is cos, then this is nothing but just this area is we calculate through integration, then we calculate this area. So full area, if you calculate, it comes to 0 because sign is changing, it is negative, so person is coming back. Okay, so we lead to how integration formulas are built. It built upon smaller things, and we saw that how x to the power k become x to the power k plus 1 by k plus 1 in the integration. And then we found the integration of sin x, and it leads to minus cos x. So this is the way bigger thing they sit upon the smaller thing. Okay, then in the first experiment, what we saw as like a person is kind of moving, and then he is moving kind of in a way that it starts from a speed and it is decelerating constantly, it is reaching 0. So in this case, kind of if I know the total duration, how much it take, and if I know what is the distance is covering, what would be the initial speed? If I know the initial speed, then so what would be its initial speed? Okay, so this would be its initial speed. If I know the initial speed, then I can calculate the distance covered at any moment. This leads to kind of we can kind of really locate a location in map with different velocity, with the velocity rotating the globe in a fashion that initial velocity would be higher and it would reach to 0. In lab session 2, we saw finding the capacitance value or behavior of the capacitor, and that behavior of the capacitor we saw it is kind of follow the integration, where any moment charge is stored, net charge is stored is integration of the I at that moment. And if I know the I equation, then I's area becomes the Q, that is the fundamental. Okay, then finally we came to equation of the capacitor, and then we took a 1000 microfarad capacitor, and we had values, and then through values we drew a diagram, and our diagram is lacking. This is the actual diagram and this is our diagram. So with time constant, we found out that capacitor is 750 only. If we are true, then we drew again, it is exactly same. Not bad. Yes. Integration is a kind of a funny way of doing the addition. Like if I have speed and I want to know the total distance covered, then I have to calculate the area. If I have acceleration and I want to know the velocity, then I have to calculate the area. Means it is one term. So, like if I have distance I covered and I want to know the velocity, then I have to go for differentiation, means division. So, integration is, we can say that it's a smooth kind of addition. Like if I go for simple addition, then we don't expect gradual changes, like within an hour. Okay, so we calculate hour by hour. Like we saw that we started moving the globe, and it started with its velocity, and velocity started decreasing. Now at every moment velocity is different. Okay, so this is smooth kind of variation. Like if it is cost, if we are worrying every second how much is the distance covered, then next second how much is the distance covered, next second how much is the distance covered. If we care about that, not inside a second, again in millisecond and microsecond, only at the granularity of the unit, then we can go for addition And if it is flat, then we can go for multiplication also. Okay, or we can go for funny way of addition. What is problem with integration? Integration is so nice, means just we need to calculate the area where the kind of the dependent variable may vary any moment. Okay, like we started the discussion with ball. Every hour I collect 7 balls or 5 balls. So at the end of hour, I see how many ball comes. We never think that if every hour we collect 5 balls, then how much is the collection at the end of 3.4 hours, 3.42 hours. We expect that the granularity is hour by hour. So this much smooth granularity, if we want, then we go for pure area. And area based addition, other name is calculus integration. So that we see what is the problem with integration. The biggest problem is we have to find the function from independent to dependent. So independent to dependent, x to fx. Fx we need to find. Okay, that is not very easy. Like we have already shown that capacitor based. So there dq by dt is the current. Okay, so if I know the current, okay, if dq by dt is current, then integration of current is total charge. So if I have current graph, any moment if I take the area, then how much total charge on the capacitor is, that we can find. But how we can find fx? Okay, so the solution is a differential equation. So whatever the way we feel that how dependent and independent variable are they are correlated. Okay, if I know their relationships loosely, then we can bring in an equation and then we can find the fx. Okay, so probably in later videos we will see differential equations, and then we see that how we find the dependent variable, that is fx, from independent to dependent, from x to fx. Once we know fx, then next question is that for each entity in fx, we have to find their integration. Like if cos comes, then it is sine. If sine comes, then it is minus cos x. So that way, and how each entity are interrelated. If it is plus, then we can have separate integration. If it is multiplication, if it is division, then how they would be related to each other. So I don't think it would be very difficult to find it out. So we'll see that how differential equation, it helps us in generating the dependent variable, or handsomely we call it fx. So in differentiation, if I do differentiation of fx, it comes back to x. Okay, so integration of, if I integrate fx, okay, so if I have fx and then I integrate and I find gx. If I differentiate gx, then we come back to fx. So this is how they are interrelated. If I have velocity and I do integration, then I get total distance. If I have acceleration, I do integration, I get velocity. If I have velocity, I do differentiation, I get the acceleration. If I have distance covered at each moment, how much distance covered, and if I do differentiation, then I get velocity. So, the reverse of addition is division. Like that, the reverse of integration is differentiation. But anyway, we'll see how we find the formula in integration so nicely we can get the area, and through area we get back what we want, and then we can kind of get our work done. Okay, so that we'll see.